All right, here we're talking about the calculations for experiment 5, Beer's law. So in number 1, you need to determine the concentrations of all the solutions you prepared. So if we go back, you weigh down a certain number of grams, and then you know the molecular weight. And so you can solve for the moles by simply dividing grams by the molecular weight to get the moles of it. And now you add a certain volume. In our flask, they're always 100 milliliters, but then for this example, I'll just say it's 200 milliliters. So we divide by the moles by the volume in liters to get the concentration. And then that's your stock solution. Now you're going to take that stock solution and dilute it. So you're taking a certain volume that has the same concentration, and we can solve for the moles of it by volume times concentration gives us the moles. Those moles are what's transferred to the new flask, and we dilute it to 100 milliliters, and we get the total volume. And so conversely, you can just use, after you make the first stock solution, then for all the other solutions, you can use C1V1 equals C2V2. And so, you know, it's going to be the volume and concentration of the pipette. And then you're going to dilute it, and V2 is always going to be 100 milliliters because that's the volumetric we use. And then you'll be solving for C2. So you're going to do that for all the flask. Hold on a second. All right. And so you can see here, then you determine the stock solution, moles over volume. And now we just do a bunch of dilutions to make solution 1. And remember, solution 1 is used to prepare all the other solutions 2 through 5. And now afterwards, you're going to then make the calibration plot. So let me just actually go back. So do all the calculations and make a data table. This actually is changed. This should be for both vernier units. All right. So both vernier units. Now you make 2 scatter plots for them. Look at the trend. And so when you make those plots, then when you plot all of them, it's going to go non-linear. And so when you come back and you have the more concentrated samples, then that's where that nonlinear comes from. So then you want to plot just solutions 2 through 5 and it should come out nice and linear. And that's where we want a good R-squared value. You should see a big difference between those R-squared values. All right, so that gets you through. Then, man, I have these slides. All right, and so then you're going to compare the 2 scatter plots, discuss the difference, and now you're going to use those scatter plots. So then using that trend line and determine the molar absorptivity. And remember, this goes back to that plot. You have absorbance equals epsilon BC. What are you plotting on your plot? What's the slope? So it should be an easy extraction of that molar absorptivity. Then 7, calculate the percent error. It's just going to likely be horrendous error. But your R-squared is actually good. So you have this conflicting information. Now on 8, then you use that trend line to determine the concentration. That's what I showed you before. Using the absorbance, go find the concentration. So here. I don't know why the cursor's not showing up. There it goes. So you have your absorbance of your unknown and simply use the equation to solve for the concentration. And now in 9, then we have the reverse dilution. And so we got a read process, and basically you're going to then work backwards. So you're going to know M3 and V3, and then work backwards to solve for M2 and M2. And then once you get M2, then you'll come and do the same thing going to M1, V1. All right. So you'll kind of daisy chain working together like that. And that should get you through it. That's all the hard calculations.